Section 2.4 introduces our last major independent rule of all the rest. So it will incorporate pieces of what we've done before in different ways perhaps, but it is a completely separate independent rule, and it's called the chain rule. So the chain rule actually applies to something you saw back in algebra somewhere, a college algebra course or a pre-calc course in high school or something. And it has to do with what's called composite functions, where there's a function embedded inside of a bigger function. So for example, maybe you had a square root where you had, a polynomial underneath it, x squared plus 2x underneath the square root. So there was something inside of the square root that wasn't just x, so you have this sort of a compounding of functions. We call them composite. And that's called the chain rule. So you see that notation of that composite over on the left-hand side, right? The g is embedded inside of the f. And then you're taking the derivative of the whole thing. So when we're trying to do the chain rule, there are two separate pieces to consider. There is the derivative of what's happening on the outside, the function here that's identified as f of x. And there's the derivative of what's happening on the inside, the part that's identified as g of x. And in fact, we do need the derivative of both of them. But we don't just take the derivative of the inside and then stick it inside the derivative of the outside, which again might be the intuitive way to do it. So chain rule, in the very much the same way that product rule and quotient rule are not intuitive, is not intuitive either. So what you see happen is you take the derivative of the outside, where the inside g of x remains embedded just like it was before. All you're doing is you're taking the derivative of whatever's going on the outside. In the verbal example I gave, it was the radical function, right, the square root function. And then you multiply that by the derivative of what would be the inside functions piece. So it takes practice, and we're going to do some practice. The first example is actually one where we don't need the chain rule, all right? If you wanted to multiply this out to the power 5, you could. It would be tedious, and you would not appreciate me signing you to do that, right? Not a chance. I mean, if it had the power 2, you might be like, okay, no big deal. Power 5, you're not going to want to do that. So on this, there are two functions, and there's something that's embedded inside. What's embedded inside here? Yeah, the 6 minus x squared. And then the outside function, there's a 2, and there's a power of 5. So everybody see the two separate pieces that are going on? Okay. So what we're going to do, and in fact what might be helpful to do sometimes, is to sort of cover up what's inside here, because as you do the first piece, it's irrelevant. I've got 2 orange blob to the 5th. That's what I have. I don't care what orange blob is. It doesn't really matter. Okay? So we're going to take our derivative, and all we're considering really is the 2 at the front and the power of 5. So what do you do when you have a 2 in front of something with a power of 5? So I have multiply the 2 by 5 to give me 10. I'm going to leave a space here. We'll fill it in a second once I reveal my orange blob. And what will the new exponent be? 4. All right, so now that piece, it goes straight inside. 6 minus x squared. And after I've done the outside with the inside rewritten as is, then I will multiply it afterwards by the derivative of the inside. So what is the derivative of 6 minus x squared? Close. Yeah, negative 2x. And that's the chain rule. Okay. Now, does it get more complicated than that? Of course it does. I gave you an example of one that's very direct at first, right? That's how we always look at that. There is a little simplification we're going to do here in a second, but this is where you would stop for the gateway, right? You have the derivative of the outside with the inside rewritten. You have the derivative of the inside. You're done. From a calculus standpoint, you are finished with this problem. Now, from an algebra standpoint, we can simplify things a little bit. In particular, I can combine these two pieces together. So my derivative can be rewritten as what? You guys are all mumbling, but I think you're mumbling the right thing. It's okay. Yeah, so now I have negative 20x, and then 6 minus x squared to the 4th. I don't need to multiply that out. That does not improve the look of the equation at all. Nothing, right? Like, that's not going to be helpful. This is where you stop. It's all cleaned up. It's all finished. This one actually looks like a quotient rule, and if you wanted to use the quotient rule to do this, you could. You could. There would be nothing wrong with that. It would be kind of messy. It's not actually the cleanest way to do the problem. But you could do this with the quotient rule. Does that make sense? The part on the top ends up being a little bit weird because the derivative of the numerator here is actually 0. Yeah, it's nothing. It's 0. So it ends up zeroing out some of the pieces, and so it ends up looking a little funky and whatever. But it's doable. You could do that. I'd like to show you how you could also do this with the chain rule, because if the denominator were, say, squared or cubed, then it's actually more complicated even yet to use the quotient rule here, but it's just as easy to use the chain rule. So when we had 1 over x before, and I asked you if we could rewrite it, you all seemed very comfortable with the idea that I could write that as x to the negative 1, right? Okay. I can apply that same rule here, but I can't apply it to the individual pieces of the denominator, right? I cannot write this as x to the negative 2 plus 3x to the negative 1 minus 1 to the negative 1. I can't do it that way. You can't pull it up piecewise. If you're going to pull the denominator up, it has to be pulled up with the entire thing together. So my entire denominator, which is x squared plus 3x minus 1, can all be pulled up and all be written with the power of negative 1. Okay? And then it actually looks quite a bit like the last problem, doesn't it? I mean, the exponent's negative, but other than that, it's pretty much the same thing we had before. In fact, in some ways, it's even nicer because I don't have a coefficient in front of it like I had the 10 here. So we're going to use our power rule. That's our general first rule we're going to be using. And much like I did before, I don't really want to, if I cover it up with the orange blob now, I can't just cleanly erase it because I wrote the words. So I'm not going to do that where I can't see it. But imagine that you can't see it like I did before, okay? Orange blob to the negative 1. That's what we have. So we're going to take a derivative, g prime of x. I got to deal with the outside function, the negative 1 part first. So what will I do?
Negative 1 space to negative 2.
Negative 1, I leave a space, and then I write it to the negative 2. That's right. And then the space holder that I've left is exactly the orange part that I covered up. So it's the x squared plus 3x minus 1. That's the derivative of the outside. Then I need to multiply it by the derivative of the inside. So what is the derivative of x squared plus 3x minus 1? 2x plus 3. That's easier than the quotient rule. There's fewer pieces to work with. If you were on a gateway and you did it with the power rule, or like this, the chain rule rather, with the power rule part of it, and somebody else did it with the quotient rule, they're both right. Your versions of your answers where they're left will look quite different. But in almost all cases, I have all the versions written on my answer key as I'm looking through, so I'll catch it and it'll be fine. It's no big deal. At this point, you'd stop for a gateway. But we're not going to stop here right now. In particular, I do still have something with a negative 2 power, right? So that piece that's to the negative 2 power, I will now move back into the denominator with a positive 2 power. And that kind of should seem reasonable because if you were thinking about this from a, actually let me just do that part of it for now. If you were thinking about this from a quotient rule perspective, having the denominator squared would show up, right? So it's quite reasonable to see that denominator end up back where it was, and now it's squared, right? And then the part at the beginning, this negative 1, gets multiplied by my 2x plus 3, and I have negative 2x minus 3 on top. Okay, we're going to do one more and then be finished for today. All right, so one more additional problem. It's going to look, again, yet a little bit different. This one's by far the most complicated one that we've looked at for a couple of reasons. In particular, it's very complicated because you see a quotient, like we did in the last one, but you also see a radical, and the quotient is embedded inside of the radical. There are two separate ways to do this, and probably they're both equally challenging for different reasons. One thing that you can do is that you can recognize this as though all of this inside is the inside function, and it's all being raised to the power of 1/2. So that's one way of doing it, and I'll do that way first, and then I'll show you an alternate approach, and you can kind of decide which way maybe fits your, thinking a little bit more directly. So this one would be 3t squared minus 2 over 2t plus 3, all raised to the power 1/2. All right, so if we approach it from the perspective that everything inside is raised to the power 1/2, then the 1/2 becomes my outside function, and I deal with that. So I will have to do the derivative of the 1/2 part. So what's going to happen with my 1/2? Moves to the front. And I subtract 1, and 1/2 minus 1 would be negative 1/2. And then what's inside is what's already inside, right? It's the 3t squared minus 2 over 2t plus 3. Now, for the purposes of the gateway, this is kind of like okay, fine, who cares? But for the purposes of what we're doing right now, this is really messy because I have a negative power and it's a square root, right? I mean, that's what it is. That power 1/2 means I'm going to have a square root reintroduced into the problem here in a moment. Now, I'm not quite finished. I still need to do the derivative of the inside, and the derivative of the inside here becomes a little bit more challenging than the other ones we've had too, because when I do the derivative of the inside here, what rule do I need to use? The quotient rule. So now I've got a quotient rule happening inside of a chain rule. All right? So my quotient rule says I take the denominator. So the denominator was 2t plus 3. And I multiply it by the derivative of the numerator. So what's the derivative of the numerator here? 6t. And then I subtract. And then I need the numerator, the derivative of the denominator. We'll do that first, which would be 2. And then I need times the numerator, which is 3t squared minus 2. And all of that is over 2t plus 3 squared. And never more than this problem before have you appreciated the fact that on the gateway you can leave it right there. I mean, seriously. Because what we're about to do to simplify, it's not going to be pretty. A lot of them we've had, they simplify really clean and it's no big deal. This one's messy. Okay? All right, so cleaning up the quotient rule part of it is probably the easiest thing for us to do. So let's actually clean that up first. I definitely do not want to multiply the denominator out. We talked about that when we talked about the quotient rule before. That's not helpful. But we do need to distribute things and clean things up on top because basically of the subtraction sign between here. That's really why we have to do that. So sometimes things will collapse nicely. So I have 12t squared plus 18t. And then I'll distribute a negative 2 through. So I have negative 6t squared plus 4. Did I get those pieces right? Good. Everything from earlier on just gets rewritten. Okay, just right beside it. No changes. If you want to separate this still to have it sort of separated off, you could certainly do that. I have 12t squared and negative 6t squared, so that's 6t squared. And then I have plus 18t and plus 4. They're all even. That's actually something that's important to notice here because there's a 2 out here in the front as the 1/2. And I will be able to simplify that a little bit. Okay, so I will need that fact here in a moment. The denominator, of course, gets rewritten to as is 2t plus 3 squared. Okay, front's the same. Okay, so mention to the 2, that's easy enough to fix. I can take this 2 out of each of these, make this a 3, a 9, and a 2. I can do that. Knowing that I have a 3t squared means that there's no way it's going to factor into something that's the same as the denominator, right? Agreed? We talked about that last time. That's not going to work. So my numerator that's in the quotient part of this doesn't need to be dealt with any further. It's as simple as it's going to get. So as messy as it looks, there's still nothing that can be done. However, there is something that can still be done otherwise. This piece right here to the power negative 1/2, which we mentioned before, has a radical component. And because it's negative, it means that I can flip it upside down. So I'm going to flip my fraction upside down to make it positive. So I have 2t plus 3. And just because it's helpful here in a moment, I'm going to write that to the 1/2 itself individually. And then I have 3t squared minus 2 to the 1/2. And this is times 3t squared plus 9t plus 2 over 2t plus 3 squared. So do you see that I've got a 2t plus 3 to the 1/2 right here and a 2t plus 3 to the 2 right there? I got to combine them because they're exactly the same, just with different exponents. So this originally, if I put it back in the denominator, would have a negative exponent, like negative 1/2, yeah? And a negative 1/2 and a positive 2. What does that give me? Like 1.5, right? So this is the number 2. 2 minus 1/2 is 1.5 or 3/2. So in terms of rewriting this, there's a couple of possibilities. The top will stay the same, but that is to say the 3t part. The 3t squared plus 9t plus 2 will stay the same. The 3t squared minus 2 to the 1/2 will stay the same. The other piece would be 2t plus 3 to the 3/2. So playing around a little bit with WebAssign, it'll probably take that as your version of your answer. If you were to do this on a test, I'd want you to do one more step. In particular, the problem started out with radicals, so your answer should have radical form to it. So here's what you would do for your answer. Let me shrink all this a little bit so that I don't have to change my screen. I don't want to shrink it too much so you can't read it. I think that's still big enough. The 1/2 is a square root, right? The 3/2 means I have a square root but a power of 3 on it. That's what it means. And so as you're rewriting that, and I'll take 2 steps to do it, though you may be able to jump to the very final step, and so that's fine. 3t squared plus 9t plus 2 on top. And then I have the square root, like I just mentioned, of the 3t squared minus 2. So that's that piece of it. And again, we don't rationalize denominators unless it's a square, just a single number, and that's not. That's an actual function, right? Then this piece right here would have a square root of 2t plus 3 cubed. When you have a cubed underneath a square root, it means you can bring it out. So think about something super simple that you know, like having the square root of x cubed. It means that I can pull one of the x's out because there's double of them there. There's 3 of them underneath there. I pull one of them out and I leave one underneath there. So I can do the same thing with this function, and that's where it would actually end, even though it doesn't look very pretty. So 3t squared plus 9t plus 2 over, and I would have a 2t plus 3, and then I would have a square root of 2t plus 3. I'm just going to put them beside each other, not because they have to be, but because it's a little bit more natural for them to be. And then my 3t squared minus 2. That would be the radical form of the answer. And this is what I would be expecting to see on a quiz, on a test, something like that, although I think that WebAssign will accept it if you stop one step before you put the radicals back in. Okay? So let me briefly tell you, and we'll do it next time, the other version of how you can do this problem. Because it's worth mentioning, because you might think it makes more sense to you to do it that way. So the other option, instead of thinking about it as a quotient rule inside of a chain, right? So a quotient rule embedded inside of the square root function, is that you can actually think about it this way instead. You can think about it as a quotient rule on the outside, 3t squared minus 2, so that you're dividing 3t squared minus 2 to the 1/2 by 2t plus 3 to the 1/2. So if you think about it from this perspective, the outside function is, in fact, the division. The quotient rule is your outside function. Whereas the powers that are going on inside of there are the chain rule pieces. Right? So this one right here, we will actually do in a slightly reverse order. We'll end up, of course, with the same answer at the very end, but we will look at that version of it next time so you can see how that plays out and see if you like that any better. And we'll stop there for today.